So now let's talk about independent events. On an intuitive level, uh, independent events are just events that don't really have that much to do with each other, or that having the information about the first one doesn't really tell you anything about having information about the second one. So how we write that formally is this guy right here. We'll say that two events are independent if it satisfies that criterion. So let's say that we're flipping a coin. Coin tosses is a series of coin tosses is kind of the go-to example, as you can see right here. It's when you have a bunch of, if I flip the coin once, that doesn't tell me anything about what I'll get if I flip the coin a second time or a third time or a fourth time or a fifth time or a sixth time. If I have a fair coin, then it doesn't matter what my previous flips were. It's uncorrelated. So that is the basic conceptual idea behind independent events. So if I want to say that, I can also talk about two just completely different things. So so if A is I flip a heads, and then B is all the so this is A is all scenarios where I flip heads. And B is all the scenarios where I roll an even number. Oh, sorry, a multiple of 3. Six-sided die. Then the probability of A intersect B is going to be the probability of A times the probability of B. These are clearly unrelated events, so we should expect them to be independent. So that means that we get this. So the probability of A is 1/2, and the probability of B is 1/3. So I get 1/6 as my probability. And the space here would be 1H, 2H, 3H, 6H, 1 tails. So just all the pairs of heads and tails with 1 through 6. So coin tosses, a series of coin tosses. One toss is going to be independent of the previous one. So we'll sometimes also represent this as branching. Sometimes it's related to the idea of a random walk. And this basic setup should look familiar to you guys from the chooses stuff of just kind of branching out with all the remaining possibilities. But guess what? I keep the same possibility over and over again because I can get heads over and over again. So and these guys go off to infinity. So this is related to the idea of a random walk. So if I were to assign the values of +1 or -1 to heads or tails, the value that I would get would end up following what's called the binomial distribution. We'll talk about that more in a minute. So show that the empty set is independent of every event. This is this is just kind of a general probability question, nothing really tying into, or not too much tying into any particular distribution. So yeah, just for any distribution. So the probability of the null set is 0, right? So if I have the probability of the null set intersect with A is a subset of omega, then that's going to be just equal to the probability of the null set, which is 0 because the null set is their intersection, which is equal to 0 times the probability of A. So therefore, it is a probability distribution. Is there any other event that has this property? Yes, there is. There's another set that this works for, and I'll give you 3 seconds to guess. Pause, whatever. And it is omega. So the probability of omega is equal to 1. So if I have the probability of omega intersect A, by definition, A is going to be a subset of omega. So that's just going to be equal to the probability of A, which is equal to 1 times the probability of A. Therefore, it satisfies our definition of independence.